the output level is slowly falling. Okay, it has to fall from VDD to ground. So first it starts at VDD and the transistor is on. Because it is on, it is also conducting the current, which we see here. So some of the charge will be removed. So the next case we are going to analyze is output equal to, let us say it has fallen to 1.5 volts. Okay, and we'll mark the same levels again. VGS equal to, okay, gate is constant 0. So 0 minus 1.5 is minus 1.5, and this is lesser than, okay, so still the transistor is on because it is at 1.5 minus 1.5 lesser than VT. Since this is a PMOS transistor, it's on, no problem. And we can do the same thing also. What is the region of operation? VDS is now minus 1.5 volts and VGS minus VT. Okay, VGS is minus 1.5, VGS minus VT is minus 1.5 plus 0.4, so that is minus 1.1. And now which is greater, minus 1.1 or minus 1.5? Okay, so VGS minus VT is greater, which means it continues to be in saturation region of operation. For this analysis, it's not necessary to find out the regions of operation. We just need to see that the current is flowing, and that needs to be checked with only transistor on or off, and it is on. But since we have a PMOS transistor, it's always good to do the analysis for the regions, because NMOS is easier to remember. PMOS, it's the opposite, so that's why I'm doing the second part also. But we know that current will be flowing, and which means the voltage level is further reduced. So it is going to further reduce from 1.5 volts also. So let us assume it is at 1. Okay, same analysis. VGS now VDS is minus 1 volt and VGS, okay, is 0 minus 1 minus 1 minus 1 plus 0.4, so that is minus, okay, on and still in saturation region. Now next, output equal to .5 volts. So now VGS equal to 0. Barely, okay, we're just reaching some sort of boundary. Now it is minus 0.5 volts, which is still lesser because our VTP is minus 0.4. So it's still okay, okay, we can still get the value for the current. And the region of operation, if you want, this time it is VDS is minus 0.5 and VGS minus VT is minus 0.5. So it continues to be in saturation, okay, and this was searching to A, B, C, and D or E, I don't know. Let's say the output equal to, now we have to be little careful, we have to choose, and I'll tell you why. 0.4 volts, okay. Now VGS equal to 0 minus 0.4 is minus 0.4, which is equal to VT, which means the transistor when the VGS is equal to VT, the transistor will turn off, because for PMOS transistor, VGS has to be lesser than VT. So that is why we chose 0.4, because we could not, I mean, you could have chosen 0.3, but it would never have gone there. As the output value is slowly reducing, it started at 2, 1.5, 1, then 0.5. Then when it comes to 0.4, suddenly what will happen is, okay, this will be our equivalent circuit. The CMOS transistor will stop conducting. When it stops conducting, current cannot flow, okay, top part is still not conducting, and this will be the final value of the output voltage. It cannot go down all the way down to 0, because like I said, it's not an imperfection of the transistor, it's an imperfection of the circuit if you connect it in this way. It's a defect that the designer has created, not the transistor itself. Transistor is still following its own properties, okay. Suppose you buy a bike and the manufacturer is saying that if you drive it at normal speeds, okay, you will get, say, a mileage of 50 kilometers per liter. Suppose you always are accelerating even when the brake is off, or always you're driving at very high RPM, or you're driving it in a very bad manner and you're getting only 30 kilometers per liter. You're always going very fast and then braking. You're always going very fast and braking. And if you're driving it like that, you might get lesser than the rated mileage. Is that the fault of the manufacturer, or is that the fault of you? Same thing here also. The transistor is not at a defect, okay. The transistor has the properties that are advertised. It is not going against any of those properties. But when we use it like this, okay, we are going to create imperfections in the circuit. In this particular case, what is the imperfection? PMOS transistor, okay, is not a good conductor of logic 0. That is the summary of the imperfection. If it is a good conductor of logic 0, this output should go all the way down to 0 volts. It is not going to go. What is the level at which it will stop? Output gets stuck at modulus of VTP. Okay, VTP is a negative number, but whatever that magnitude is, at that particular value, the output will get stuck. It will not be able to go below that. So this is a problem with PMOS transistor when you put it in the bottom part of the circuit. Now, just to make ourselves sure, if the PMOS transistor is in the top part, we will make sure that there is no problem. So we will quickly redo the analysis, okay. So I'm going to put the PMOS transistor on top, and while I am doing that, I want you to think of which terminal is the source and which terminal is the drain, okay. Input has to be 0, because that is the only case in which a PMOS transistor will be conducting, so that will not change. And bottom also, I don't care, okay. I don't care what is there, it's just an open circuit. And in this case, what is the transition of the output? Output has to transition from okay, output has to go from 0 to 1. So that is what we want to verify. Does it go all the way up to 1? The perfect one is how much? VDD, okay. It should not stop at, say, if VDD is 2 volts, we will use the same numbers. It should not stop at 1.7 or 1.8. It should take the output all the way up to VDD. We want to see if the PMOS is going to be conducting up to that particular point, which means that this type of connection is fine. That created a problem, okay. Is this fine or not? We will verify. So now comes the question, which is the source and which is the drain? Only if we mark that, this VGS VDS analysis we can do. So what is the direction of current? Is it from output into power supply, or is it from power supply to output. So it is at 0. It has to be charged to a positive value, say plus 2 volts, which means that some charges have to be supplied to the output node. It cannot come from the bottom because that is open circuit. So those charges have to be supplied from the top, which means that the direction of current, because current direction is nothing but the direction of the positive current, that has to be from power supply to the output node. So some charges, say some 25 microcoulomb, they have to be supplied so that at that particular node, if I keep a voltmeter, I should get 2 volts, which means they have to supply from the top. And since that is the direction of current, holes have to flow from this terminal to this terminal. So this is the source, this is the drain. So now we can do our analysis. Start with, we will do it a little bit faster. We will not worry about the domain, okay, that is linear or saturation. In every case, I want to verify if the transistor is continuously on till the output node has charged to the perfect value. Okay, so we will start. Output equal to 0 volts. This is the first. So each value we just have to write VGS equal to 0, 0. Okay. So 0, 0, S. S connected to VDD. So VGS equal to 0 minus okay. So this analysis is somewhat easy because VGS is a constant value. VGS, gate I am giving 0 volts, source is permanently connected to 2 volts. So VGS does not change for the analysis at all, and that is part of the solution also. Every time if the drain voltage is changing, it doesn't come anywhere into our VGS lesser than VT equation. So whatever the value of the drain voltage, okay, the VGS is always lesser than VT. So we will do a few more examples. Let us jump to 1 volt, okay, because 0.5 is the same this thing, it doesn't have any extra analysis. No change, drain voltage has gone from 0 to 1 volt, but VGS doesn't change at all, okay. So VGS is still minus 2 volts, it's still lesser than VT. I can continue to operate the transistor, or rather transistor will continue to be on. Okay, 1.5 volts, still nothing. Let's say you want to try 1.6 also, because last time if you remember in 0.4 we stopped. 1.6 volts equal to VD. Okay, VGS equal to still minus 2 volts, lesser than VT, continues to be on. No change at all in VGS anywhere because VD is increasing, VS is at a constant value. So now let us do the case of the perfect value 2 volts, and here VGS equal to minus 2 volts. Okay, no change, still it is at minus 2. What is happening? No problem. Is lesser than VT, so the transistor is on. Okay. VGS equal to minus 2 volts, it's lesser than VT, transistor is on. If for this region alone, let us try to analyze what is the region of operation of the transistor. So we want to compare VDS and VGS minus VT. So VGS minus VT is minus 2 minus of minus 1.4, so that is minus 1.6 volts. This is VGS minus VT. And what is the value of VDS for case E? VDS equal to 0, because VD is 2, VS is also 2. So which is greater? That is VDS is greater than, okay. Now what is the region of operation? Region of operation is linear. This is the linear condition for a PMOS transistor. Okay. So now why I did this is, I want to tell you that VD cannot go over 2 volts. I am going from 0, 1, 1.5, 2. Can it go to 2.5? Why it cannot go to 2.5? Because at this particular point, when it touches 2 volts, the transistor is on, no doubt about that. It is in linear region of operation. So if you remember the equation, current equation for linear region of operation, NMOS and PMOS, it is the same equation. Okay, the current equation is mu n C of W by into VGS minus VT minus VDS by 2, the whole into VDS. Since VDS is 0, the whole thing becomes 0. So once it has reached 2 volts, okay, which means that enough charge has been supplied, and this point equal to this point is 2 volts, the transistor is still on, okay, but current doesn't flow anymore, which means that it has to stop at 2 volts. It cannot go from 2 to 2.1 because no more charge will be supplied. On both sides, the voltage is the same. Since there is no voltage difference, charge cannot flow. So this is the analysis, okay, to tell us that it will reach 2 volts, plus it cannot go above that also. So here, this is not a bad thing, it has come to the correct perfect value. So this is the main reason why PMOS transistors are a good fit on top here. So the summary is, okay, this is the same thing. I'm drawing it straight, now I'm just drawing it sideways, but it doesn't make any difference to the circuit, okay. Before they were flowing only because of the electric potential, there was no gravity in the picture. So here also there is no gravity, due to electric potential they will flow, okay. So this is very important. Logic 1, which is, I can say, equivalent also, okay, to VDD. If you give to the PMOS transistor, at the output of the PMOS transistor, you will get the same value. Strong 1, that is what it is called. Strong 1 is equivalent to the voltage amount or the voltage level of VDD. Okay. Now, okay, this is the main problem. If you give a 0, okay, the output will be a weak 0. What is the meaning of weak 0? It means that it is at a level higher than 0 volts. And what is that value? Weak 0. Okay, in fact, I can erase this also and put it as weak 0 equal to, or not equivalent, weak 0 can be anything, but the problem is it is not at 0 volts. Okay, this is the summary for PMOS. What is the summary for NMOS? Okay, input I am giving 0, I am getting strong 0. Strong 0 is nothing but 0. Okay, so that is the good case. This is the problematic case. I am giving a perfect value VDD, but I am getting an imperfect value at the output, and this is called as a weak one, and in particular its value will be VDD minus VTN, because VTN is always going to be a positive number. That value will be always lesser than VDD. Maybe if VDD is 2 volts, it might be 1.6 or 1.5 or 1.7 or something, but lesser than VDD. So this is why it is called as a weak one. Okay, and now most important thing, based on this analysis, two types of configurations we will ignore. Okay, we will avoid, rather than ignore, we will avoid those types of configurations. There are 4 different configurations, right? 2 we will ignore and 2 we will reuse again and again. Which 2 we will use? Wherever the output is at a strong value, we want that. Okay, wherever the output is at a weak value, we don't want that, because as we will see later on in this unit also, any output that is produced in our circuits at the theory level, okay, at least at the design level, we want those values to be at perfect levels. We don't ever want any circuit, okay, to produce values that are at imperfect levels. And this is the problem I mentioned. This is one of the problems with the NMOS only or PMOS only technologies. In NMOS only technologies, what is the problem? Okay, the output value can never reach VDD. There are some design techniques, as we will see, to make it go close, okay, but never perfect. The same thing with PMOS only technology. The output can never be at 0 volts. There are some techniques to make it go low, but it will always be at 0.2 or 0.3 volts by design. That is at the circuit in the theory level. That is in my design itself. I am having these sorts of intermediate levels for the voltages. So we generally don't want to avoid those. So in this thing, we don't want this type of configuration to come in the circuit. we don't want this type of configuration to come in the circuit. So every time we design, we will use only these two cases. So that is why all the NMOS transistors will always be in the bottom part of the circuit. All the PMOS transistors will be in the top part of the circuit. So that is the main rule when we are going for designing our gates. So now that we have these rules, let us look at the structure of a CMOS gate. Okay. Okay. So okay, so the type of circuit family is called as static CMOS circuit design, okay, or static CMOS circuits. This is the name of a family. There are other families also, as we will see. There is a dynamic also, because if there is static, there has to be dynamic also. And already I mentioned briefly, there is another one family called pseudo NMOS. So the static CMOS is the first and by far the most common. Okay, so if you take any digital circuit, for example, 99% of the circuits will be in static CMOS family. The rest will be in dynamic. Today nobody uses pseudo NMOS, but dynamic circuits are also going to be used, but to a smaller extent. Okay, and we will see the reasons for all that definitely. But first, let us look at our first circuit family, also called as static CMOS circuits. So static CMOS circuit family, very simple rules. There are some rules, okay, and the any circuit that you design using static CMOS family should follow these rules. What are the rules? There should be two separate networks. Okay, there should be one which is called as a pull up network, and there should be another which is called as the pull down network. And the inputs, okay, what is the meaning of this line? Generally in computer organization, when you have a line like this with this is a bus. Bus is a many inputs together, okay, so maybe 8-bit, 16-bit, whatever. But here also same thing, not necessary that only one input you can give. You can give 2 input, 3 input, how many ever inputs based on the functionality. It can be 3 input, 4 input, but the inputs have to be given to both the networks, and these are networks of transistors, okay, which means that there can be definitely more than one, plus they can be in series or in parallel. So I'll write down some of these things. First rule is that inputs are given okay. We don't call it PU network and PD network. It is just PUN for pull up network and PDN for pull down network. Inputs are given to both the networks. This is the first thing. Second thing is output is connected to VDD okay. So this is almost a guarantee based on the configuration. Output, okay, if the output has to go from 0 to 1, it can only go through this network. There's no other connection, right? Output, if it goes in this direction, cannot go up to VDD. These are inputs. This is not an electrical connection. We are not allowed to drive these wires. Somebody else is supplying those signals. So through this side, it can go only to ground. Through this side, it can go only to VDD because of the nature of the connections itself. So that is almost a guarantee. But because of this, okay, because of point number 2 and imperfections discussed, okay, PUN okay, this is the main outcome. We have divided the functionality into two networks, okay, and because the top network, what is the meaning of pull up network? What is getting pulled up? This is of course VLSI circuit, so nothing can be moving. In generally, this is the one of the truths about any electronic circuit, okay. There are no movable parts. The only thing that move are the charge carriers. Nothing else moves in the circuit, and this has a lot of effects. Because of this, the circuit is more reliable, because as you know from our mechanical devices, whenever there is moving parts, there is more wear and tear, okay, and whenever there is wear and tear, there is going to be failure. And in mechanical parts, they are big enough, we can actually repair them. But if that happens in electronic circuits, you cannot repair them. If you can replace the whole IC if it is on a PCB, and if that is not possible, there is nothing else you can do. So that is both, it's a advantage to a much larger extent, because the failures are not so common. So it is definitely an advantage. There are no movable parts, okay, and also many more advantages, all of the same thing. It's faster, it's cheaper, the form factor, the size is much lesser, everything is an advantage. And what does this means the voltage level is being pulled up or pulled down. That is the output node, it is at some voltage level, right? Pull up network means it is responsible for pulling up the voltage level for the output node from 0 to 1, and pull down network means it is responsible for pulling down the voltage level from 1 to 0. That is what PUN or PDN means, okay. And because of this, this is the most important conclusion. This pull-up network. It can have 5, 10, 15, 20 transistors, no limit on that. But every transistor inside this has to be only a CMOS transistor, because anywhere if I put a NMOS transistor, the output might get stuck at a bad value. And same thing for the pull down network also. I can have 10, 20 transistors, no problem, but all of them have to be NMOS transistors. Any PMOS transistors here, output might get stuck at a bad value. So all the analysis we did, strong 0, strong 1 and all that, for getting this type of, for justifying rather this type of connection. Okay, so this is the first thing, and some more rules are there. Okay, rule number 4. Very important rule also. Okay, so first, what is the meaning of a network being conducting? We know what is the meaning of transistor being conducting. Okay, but network being conducting is just means that there should be at least one path. Okay, we have some examples we saw when we looked at the NAND gate, NOR gate, etc. If there are 3 parallel paths, suppose a network consists of 3 parallel transistors. Okay, network is conducting means what are all the options? One transistor conducting, 2 transistors, any 2 transistors conducting, or all 3 transistors conducting. That is the meaning of network is conducting. That is what we mean for the pull-up network and the pull-down network. The network is conducting means there should be at least one path. Okay, and if there is a path, then definitely there is a connection between output and ground, or output and VDD, depending on the network. And that is why this point is very important. The design of the pull-up network and the pull-down network should be such that exactly, okay, this is our responsibility. We cannot put transistors in random and say this is a static CMOS gate, go use it, because this rule might be violated. There might be a case that pull-up network and pull-down network are both conducting. I have given the inputs and I have designed the gates in such a way. You want to see a gate? I'll show you a gate, no problem. This is satisfying all the requirements of static CMOS circuit design except rule number 5. If I design a circuit like this, okay, rules 1 to 4 I am not violating. Inputs are there, there's pull-up network, there's pull-down network, only PMOS, only NMOS. But if you have these 2 input cases, suppose input is 0, 1, okay, which means that this becomes a closed circuit, this becomes a open circuit. Here this becomes open, but this is the equivalent circuit for 0, 1, okay, and its mirror image is the equivalent circuit for 1, 0. But in both the cases, where is the output? That is our question. What is the value of the output? Is the output 0 or 1? Because through this network, output is connected to VDD. Through this network, output is connected to ground at the same time. That is the problem. It's not that for one input combination is connected to output, another input, that's fine. But here at the same time for input 0, 1, there is a connection to VDD and to ground. So output, for example, might be, we don't want this. VDD by 2, okay, is not a recognizable value. If I supply this to another gate, because in CMOS, VLSI, the outputs generally are supplied to another gate, okay, except for the primary inputs and primary outputs, there are so many stages. So generally anything we generate might be given to another gate. If I am giving this signal to another gate, the circuit will completely malfunction, because this will be neither at VDD nor at ground. All our VGS minus VT analysis, everything will go wrong. It will be at a completely wrong value, which cannot be. It's like saying, there's a very famous scientist, I forget his name, but somebody gave him some idea or some theory, and his comment on reading through that paper or whatever it was, he said that this is so bad that it is neither right nor wrong. Okay, this is almost like that. This value is so bad that it is not VDD or it is not ground. And these types of values, I mean, we looked at some imperfections, and as we will see, those imperfections are okay because we can do something about them. But this is completely not workable. So this rule number 4 is to avoid this type of situation. It should be connected exactly to one of them. It should not be connected to 0, okay? Not be connected to both. We will see. There is a, like I said, there's a separate gate called tri-state gates, but that is a separate class also. But for now, okay, exactly one of them should be conducting, so that the output is connected either to 0 or to VDD. Okay, so this is all. But now the question is, actually two questions. One question is, I have some function, okay? How do I design the circuit? I don't know anything about that yet. I have some function, say A, B plus C. It's not an AND gate, it is not a NOR gate. It has some ANDing, it has some ORing, but where is the, how to do it, right? We don't know that yet. That is the first thing. Second thing is, how do I satisfy this rule every time? What do I put, how do I design my pull-up network and pull-down network such that both of these rules are satisfied? Okay, so next we will see that one. Okay, compound, nothing too complicated, just means that any arbitrary logic function, okay, how do we translate it into a circuit? Again, the gate is the logical expression, okay. I am not going to, for example, if I have some AB plus C, okay, I don't want a gate that looks like this. This is not my objective, even though it says compound gates, okay. What I am looking for is the circuit. In static CMOS family, how do I follow all those rules and design my circuit level diagram? Okay, so first is recall NAND, okay, NAND bar NOR. We drew the circuit for each of those 2 input cases, 3 input cases, etc. What we are trying to tell here is, therefore, if function has okay, this is the, from these two gates we drew the circuit, okay, and we can't keep NAND and NOR, we knew it, so we drew it. But any particular function, I cannot keep drawing arbitrary gates, calculating the truth table, finding out what is the function, and then finally I'll take forever for even simple functions. So the way to do it is, remember the structure of NAND and NOR, okay? And in NOR gate, when I have A plus B, okay, and I have put the bracket here because I can do, instead of A, I can do A plus C also, not necessarily just A, okay, we will not worry too much about that, but whenever I have two terms being ORed, I have to put two NMOS transistors in parallel, and automatically where I will put the NMOS transistor, it will be in the pull down network, it cannot be in the pull up network. Similarly, if I have two transistors, two terms in my logic function can be anything, okay, but I will build them term by term. By seeing the smaller and or terms, we will slowly go to the top level from the bottom level, okay. So if there are two terms being ANDed, you remember the two input NAND gate, okay, the two NMOS transistors were in series, so it was A and B, right? So here also I have to put those two transistors, NMOS transistors, in series. This is the first thing that will help me, okay, design my pull down network. Whatever function is there, series parallel, divide it into series and parallel. If it is in parallel, you put them in, divide it into AND OR, because now I'm looking at a logic function. Whatever logic function is there, okay, you see whether it is AND or, and then you keep putting terms based on the individual terms in AND or. Now that will give me my network. Now how to satisfy rule number 4, which says that neither two or none should be conducting, always only one should be conducting. For that we have second this thing. Okay, so the first rule, if you follow these instructions or you follow the first rule, your full pull-up network, pull-down network, because we are looking at only NMOS transistors. Okay, we have created the full pull-down network for the function, but like we know, static CMOS cannot work with just pull-down network, which means that always the output will be going to 0. Output will never go to 1. So we need a pull-up network also. The pull-up network, you don't have to look at the logic function anymore. That is what we are going to say. To satisfy that rule number 4, which is exactly one of pull-out network or pull-down network conducting, create the pull, sorry, I made a mistake again. Create the pull-up network such that okay, this is the simple rule you have to follow so that we will never have the bad voltage levels. VDD by 2 we never want. How can we guarantee that? Just see the pull down network which is completed. Okay, pull down network is completed because we have used these two rules and we have created the full pull down network. Now no more look at the logic function, just see the pull down network. Any transistors that are in parallel, okay, suppose I'm having A and B NMOS transistors in parallel, you make them A and B in series in the pull up network. Okay, any transistors already in series in the pull down network, A and B in series, you make them A and B in parallel in the pull up network. So just keep following these rules, convert the full pull down network into a full pull up network. That is what we are saying here. Any transistors in series, okay, will become parallel. Any transistors in parallel will become series. And obviously this is pull up network. So all these transistors are what type? They have to be Cmos transistors. Pull up network automatically Cmos transistors. So no NMOS transistor confusion at all. Every NMOS connection we have to see and create the opposite. And the reason why this works is basically this all goes back down to De Morgan's law. De Morgan's law says that A plus B the whole bar equal to A bar plus B bar. So here also same thing will work. The explanation is there in the book, but this is the procedure. Okay. And last but not the least, okay, point number 3. This is very important because a lot of people forget this. Circuits created this way are naturally inverting. This is very important. Okay. I hope the recording is still on because this is a very important point. Circuits created using these rules naturally, suppose I am starting off with some function f equal to ab plus c. I follow all these rules. I created my pull up network, pull down network. I have the output. Okay, the output is actually ab plus c, the whole complement. This is very important to remember because if you remember our first NAND and NOR, naturally we didn't get ab, we got ab the whole bar. Similarly, we got a plus b the whole bar. So whatever steps we are doing here, we will get the complement of that function. Beyond that, if you want to go, you have to add a inverter. If you already have the complemented form only, then you can stop there. Okay, so this is very important to remember this point. We will again mention this in the examples also. So I think the recording would have stopped by now, so we will also stop.